Final day, day 12. What is it? It's a big one. Hi and welcome to another episode. What we've got here is the PiHut Advent Calendar. Let it glow. I'm on to day 12, and as I've already said, it's a big one. Oh, I know what this is. Do you? It's a display. It's got the controller board on it already. I've used things like this before. You may have done as well back in the day for the likes of, well, I don't know, these sort of screens. People like putting these on the front of their Xboxes. You've got other people doing them on, what was the Amigas for the Gotex. That's the thing, Gotex. There's a display for Gotex. It's got a little film on it to protect the screen. I'm going to leave that on. So it looks like it's dented there, but it's not. It's just the peely thing to protect everything. But yeah, there's a controller board on the back. I remember picking a few of these up and having to solder them myself, which is fun because you had to solder all these pins and then all these pins. But anyway, that's me rambling. Let's get on with what's day 12. Well, what is it? Let it glow, Maker Advent Calendar, day number 12, dazzling displays. It's the final day of the Let It Glow Maker Advent Calendar. Today we're playing with a liquid crystal display, an LCD, which is a bit of a hybrid as it's an LED backlight, kind of blinky, and can also information from our program, which makes it double the fun. What else does it say? It's another component that's hugely popular with makers around the world because of how useful they are as a project display interface to show data and build into projects. Let's get it set up. So it's saying box number 12, contents. In this box you will find a 1 times 1 lot of, a 16 by 2. No, it's a 2 by 16. With an I2C backpack. So we've played around with I2Cs before, haven't we? Not be one as fancy as this, but we have played with them. By the way, it has jumpers and twiddly things on it. Don't play with that unless it tells us to. In the meantime, leave that alone. Important, the rear of the LCD should have a 2-pin header with a little back jumper or joiner already fitted to them. If not, check the bag for this and pop it on the 2-pin header. It's talking about this thing over here. 2 pins. It's important that they're like that. Right. Funny, I was already telling you that. Right, let's move. Where's the mouse pointer gone? There we go. Today's project. Today we're going to show you how to wire the LCD up, then take you through the library to show you all the functions you can use to show different data and characters on them. We'll bring that to life with some fun projects, and then it's over to you to make whatever you want. Whatever you want! First, let's talk about the display. What is an LCD? In the box is an LCD, a liquid crystal display. You may have seen displays like these on various terminals and machines on your travels. They're not as common as they used to be, and the world continues to switch to little touch screens for devices, but they're still perfect for maker projects. We won't get into how liquid crystal displays work or how they show characters. That's heavy stuff and complete lesson in itself. Just know this. It all started with carrots in 1888. With carrots in 1888? Well, click that link if you want to find out more. Backpacks make life easier. You'll notice that the front of the LCD has lots of pins, 16 in fact. Additionally, you'd need to wire up the most of these pins in your microcontroller, which was a bit fiddly task. However, the LCD in your box includes an I2C backpack. These backpacks connect to the LCD pins and provide us with a much easier I2C interface to control them with. The backpack allows us to connect the LCD to our Pico with just 4 pins. Construct the circuit. As always, make sure your Pico is disconnected from the USB cable when working on the circuit. Is it? Is it disconnected? Yes, it is. Prepare the bedboard even. Remove the membrane keyboard and block LED from yesterday, but keep the RGB LED strands in place. Your starting point should look like this. Okay, let's move that up there for a moment. Yep, that's all there now. Got lots of bits and pieces up here now, haven't we? Not put them all tidy away in the boxes. Who cares? We're working on them. Right, so it should look like this again with the wires. Well, I'm not going to make the mistake I did yesterday where I actually undid that wire. So we've got red, grey and green we're looking after. So all the rest of them can just come away. There's some rat nest of wires. Keyboard, be careful we're moving the keyboard because, as I said, these ribbon bits can be very delicate. Just put that there as well. Move the resistor to a place where we'll easily find it, and the block LED. So we have got the little setup like it displays on there. Connect the LCD. Today you have a different set of jumper wires made to female. We're going to plug the female ends into the LCD backpack and the male ends into the breadboard. It's usually best to separate the wires to allow them to easily reach the pins we mentioned below. The two pins on the other side of the backpack should already have a little black header on them, just enables the backlight LED. If a little black jumper is in your bag or not connected, pop it on with these two pins now. So the doubly making sure that you do that, because otherwise you might think your screen's undone. So anyway, these it says to separate them, so carefully do that. Okay. Let's get going. Connect the ground to the LEDs, so the LCD to the ground pin of the Pico. We're using physical pin 38. Okay, let's try to have a look at that then. So when we're looking here on the screen, you can see the pins down the side. So the top one is ground when you can see the screen, and basically all the soldered parts across the top here as well. So the pins off to the left, ground. Let's what colour they're using. They're using black wire. Okay, so I'm going to use the green wire on the top pin. It shows in the diagram there, and we want that to go into let's make sure that this wire from yesterday is in I1. I nudged it yesterday and messed it up, or I put it in the wrong place in the first place. But make sure that this wire, this red one, is on I1 from yesterday, and we're putting this green wire onto J3, and we're going to put the brown wire, the VCC, I'm going to put that onto I1, and then we're going to take the blue wire and that goes onto the SDA, and that goes across to, where did it go to? B19. Make sure it's in B19 and not A19. And we'll take the last wire, SCL, and that should go on to B20. There we go. So we have a little display. I'm not too sure. I'm going to put it there. Hopefully it can still be seen. Let's double check on those wires up here. So this, the SDA goes off to physical pin 19. SDA 19, yep, that's been done. And physical pin 20 for the SCL. They happen to be using ground, 5 volt, V bus, GPIO 14, GPIO 15. Says here We're using this pin for the strand lights already, but there are 2 available holes you can use or make a rail if you prefer. For the SDA, this will be shared with the temperature sensor. There are 2 available holes next to the pin on your breadboard, and the same for the other one. Okay. Connect the temperature sensor. That's this thing. We'll fit our temperature sensor to the top left of the breadboard with the waffle side. I know what they mean, all the little holes and everything, facing forward, the same as day 9. Okay. Connect the left pin to the 3v3 pin. The physical pin is 16. So we want this on row F, and we want the left leg to go into 27. So F27 for the left pin, and then the rest of them should just all go in. But now we need to wire it up. So let's get a red wire, whether they're hiding. Put them both at the same time then. We'll go from J27 on the top board until the bottom board. Where do we go? Pin 36 is all the way over here. I want that to go into J5 of the lower board. Okay. And then we need a blue wire from J26 to A19, which is that one. And then we want grey one, but we don't. Have we got grey wire? Yes, we've got grey wire. J25 over to A18. And then we want a yellow wire. J24 to, where's that one go? A20. That's those ones. I've definitely done it correct this time around. It was a bit of a hiccup yesterday. I want to make sure I'm doing the things correctly. Right, we installed the code library, like just we did on day 9. The temperature sensor, we need to install a code library to use the display. This time it requires us to install 2 files to our Pico, but it's the same process. We're going to be using the exact RPI Pico I2C LDC library by GitHub user T-622 Tyler Pippi. This library adapts code from another LCD library to make it work nicely with the Pico. Marvelous! So on with our 2 library files. As the library code is rather long, we'll be using direct to the pages containing the raw versions of the code to copy and paste into Thonny. We'll be directing you to pages containing the raw versions of the code to copy and paste into Thonny. Correct. Okay, fine. Just want to doubly make sure I was reading that correctly. So we need to go off to this link. And it's telling us that we can do Control A, Control C, and then when we get to Thonny, we can do Control V. Okay. So we click that link. We can do the Control A and everything like that, but we can also right click, select all, right click, copy, right click, paste. And we can close this down. And now we need to save the file into Pico. File, save as lcd_ipa.py and close the tab. Right, we've got it all connected. First things first, click stop, make sure it's hooked up. Now we can click file, save as, Raspberry Pi Pico, and we need to call it this, the LCD underscore everything. So now we press Ctrl V, click OK. Right, it's copied that across. And then we need to do the same for the next one. So we click it, right click, select all, right click, copy, close this one down, start a new one, right click, paste, click file, click save as, Raspberry Pi Pico, and what was the name that we had to do it as? Pico underscore I2C underscore LCDPY. Okay. Press Ctrl V and click OK. There we go, and then we can close that tab and we'll start a new one ready for next time. Important, as before, once you save both library files to Pico, close the script tab down by selecting the X in the tab. But we've done that, okay? Before we start coding, have you tried turning it off and on again? Our circuit uses two I2C devices, the temperature sensor and the display, on the same I2C bus. More on this later. We found that very rarely we need to unplug our Pico USB and plug it back in again to get it to find both IC2 devices addresses properly without showing an error message, EIO, and bad pin. Most of the time it doesn't happen, but it does. If it does, now you know what to do. Well, that's easy enough done, isn't it? Let's preempt it. Unplug, plug it back in again, press the stop button, and hopefully that solves the problem. If you run into any issues at any stage, double check your wiring first, then disconnect your Pico from the USB port, leave it for a few seconds, then plug it back in again. Okay, we'll definitely do that. Right, test. Activity number 1, test, program and tweaks. We need to make sure that everything wired up and working as expected, so let's push some simple text to the LCD to ensure the display is set up properly. This script simply shows "Hello World" on the first row of the LCD whilst printing text in the shell window. Unlike other days, we're not going to go into how the code is doing this yet. We'll cover that in the next activity. This one is purely to get our LCD ready to play with. Setting the contrast. One of the main reasons we're running into the first test is allow us to check and adjust the display contrast. On the rear of the display is a little blue square with a cross in the middle. This small potentiometer, which we may or may not need to adjust to allow us to see the characters on the display. Under the script below, check that Thonny is showing print line, display is now showing characters, then check the front of the LCD for "Hello World" on the first row. If there's no text, if you don't see any text or lots of white squares, use a small screwdriver to gently adjust the potentiometer, usually clockwise, a very small amount at a time. The potentiometer is delicate and does not keep rotating. It will stop at both ends of the range, so please do not force it. Yes, I realise I've overemphasised this with them, but you may realise that's something I did once. Right, so here's the code. Let's copy that code across, stick it in. It told us not to worry about how stuff works just yet, so let's just run the code. Hello world. Let's zoom in. It worked perfectly fine for me. I didn't have to do anything. It's all doing it. There we go. I'll zoom out a little bit so we can see the board still when I'm playing around, but there we go. Hello world! Didn't have to adjust anything. Great. But the little thing that it's talking about for adjusting is that blue thing there. Tiny little screwdriver. Basically it becomes one of those things you could do with maybe some help, even someone holding it while you're turning it, or put it face down, turn it a little bit, turn it down again, keep going, keep going, keep going. But you should end up with a blue background and white text. Right, so we can stop that now. Move on to the next bit. Wait a minute, did it have to display that there? Did it? Let me run that again. Oh, I did. Display is now showing characters. Yep, sure is. Sorry, I missed that bit. Right. The everything script. Time to explain how to use this library with the LCD, and we're going to do things a bit backwards this time, running the code before we explain how it works. The library comes with a test file showing capabilities. However, we want to break it down a little, space things out and add lots of excessive commentary to give you something super duper clear that you can almost refer back to as a guide. Grab the example code below and run it in Thonny a few times while trying to follow the commentary. Then we'll explain each part in a moment. Okay, right. So get rid of this one. Get a new one going. Copy the code. Paste it. Let's have a look at the code. Well, I'm assuming this is the bit where we've imported the libraries. Something about time as well, we're importing time. The SDA is on pin 14, 15, and the bus is on 1, and the LCD address is that. Which is something we learnt the other day, isn't it? The stuff and I explained. I know that's hexadecimal, but where it's pointing to, I'm not too sure. Number of rows 2 and columns 16. Hence why it's a 2 by 16, not a 16 by 2, it's a 2 by 16. LCD, I2C, well, there's all the fancy stuff of where it's sitting. Something about a frequency of 400,000. We've got other stuff of what we've used before. It's talking about where it is, as in that's getting pushed, all this is getting pushed into there. The LCD address, that one, number of rows and number of columns is from here as well. So we've initialized everything. Our variables, we've got my string, a string of variable. Integers 44, and the float is 9.445589. Don't know what it's being used for. Just a function to sleep and then clear the LCD. Save lines after each example. Okay, so let's clear in the LCD. Says the real program start. I am a string. Okay, so that's some basic text again to get displayed. This is how you clear the display. Do this before you send new data to the display. So every time you've sent something to the screen, we need to clear it before we send some more. At least for a fresh update. This is how you move the cursor. We moved it to the second row, first number in the column, and the second number is the row. So your XY coordinates. And the first one is 0, 0. 0, 0 is the first column and the first row. Okay. So this is going by columns and rows. Clearing the LCD again. This is how you show a variable. Variables can be strings, integers, or floats. str converts them into a string. Here is the 3 examples, because of course we can't send an actual integer to it because that's just a number. We need to send strings, we need to send characters. So the way that the computer thinks about it is if you haven't told it so, it will use it as a number or a float, an integer or a float. but we need to display the string, so it converts that into a string so it can be displayed. So it converts into characters. Okay, this turns the backlight off. This turns it on. This turns the standard cursor on, and this turns cursor off. This turns the cursor, blinking cursor on, and a blinking cursor. Oh, typo. This turns a blinking cursor off. Let's edit that, and that runs it. Okay, so not that really mattered, but it's a typo. They've obviously cut and paste and not bothered to watch what they were doing. Right, let's run it. But I'm going to zoom in a little bit because obviously what we need to do is see the screen. So let's see what the screen does. The wiring, we already know what's happening there. I can always zoom back out again if they get us to do some different rewiring. Right, so I'm pressing run now. I am a string. Second row. String variable. 44. 9.445589. And it turns it off. And it turns it back on again. Cursor. Cursor off. Blinking cursor. And blinking cursor off. That's it. So there we go. I can stop that now. And we understand enough now, don't we, with this, because basically that str converts the string into a string. I don't think it actually needs to be done there because I believe my string, where's the bit that converts it to my string? Yeah, up here. My string is a string variable already. So this bit here, they've done it for the sake of neatness, but let's see what happens if we delete this. I realize this is going a bit off, but I'm trying to prove a point and I want to know if I'm correct. So since the string was already, my string is already a string because we put it in quotations before up here, that should be fine. So I'm going to run the program again now. So I am a string. Second row. See, I was correct. There was no need to do that there. They're just doing it to try to make sure it is a string. It's one of those things of sometimes putting commands in, if you're not worried for trying to save space in the amount of memory that you've got to play around with the program, it's sort of, especially for beginners, to recommend that you do it that way so that you keep tabs on what you're trying to do. But we've saved a very little amount of memory running this code like this. But I'm going to put it back now, just so that it is as they had it, even though they're probably just going to delete it now anyway. So we'll stop it now because we've got to the end. How the library works. The code above sets the LCD up to run through lots of the most useful functions that you'll need when making projects. Let's talk it through. Library setup. First, we must import the two libraries files we've created. Okay, fine. We need to tell our programs which I2C pins we're using, as well as which I2C bus. Notice the Pico pin out. The blue I2C pins are either I2C 0 or I2C 1. This is the bus number. Okay, let's have a quick look at the pinout again. Like what we've done before. Let me go drag it across. So where are we? Where did it say? I2CO. There we are, aren't we? I2CO, I2C1. So there they are over here. Anyway, that's what that code is. We've already looked at this before when we were looking at it before. 14, 15, and 1. Now we tell our program what the LCD's I2C address is. We found that for you it's 0x27 followed by the number of rows and columns in our display. This is 16 by 2 display, 16 columns, 2 rows. So we use 16 and 2. I see why they're displaying it like that now, because they're trying to well, that's how they've done it. But they've still written the code like that. It's not. It's 2 by 16. It's always referred to. So when you're looking for a display, look for a 2 by 16 if you want a different color. Not 16 by 2. Whoever's done this doesn't really understand that, or has forgotten. Then we have some lines setting up the I2C LCD with information. So that's what this stuff here was with the 400,000. Library functions, let's run through what each of these functions do. All these features are example described above. The first one is really important. Clearing display. When using one of the functions below to show something on this, you should usually clear the display first using lcd.clear close bracket, open bracket, close bracket. If you don't use LCD clear before sending the next thing to the screen and display, you'll show that the new data right on top of the old data, and in some scenarios that can leave old characters lurking behind and makes a mess of things. Sending the string. So there we go, sending the string. So you see, the very first, they're pointing out I am a string. So when I messed around and changed this, there's no need to do that, because they're already doing it. They're just trying to prove a point about something. But anyway, to send the variable to display, we use the following line. Variables can be strings, integers, or floats, because this line converts them to a string using str, short for string, obviously. So that's what it's doing. Send the string alongside a variable. This isn't strictly a feature of the library, just a different way to structuring what goes inside these brackets, but it's handy reference when we want to show you an example of string next to a variable. So yeah, basically string plus string variable, or variable string or string. So we can put things together if we wished. Moving the cursor position, by default any data you send to display is set to 0, 0, the first column, first row. Sometimes you'll want to show the data in different positions. So to do this, we'll line below, before we send the data, the first number in brackets is the column and the second number is in the row. So this is why they've done it by 16 by 2, but it's not what you look for. So I can see why they're trying to make it easier to understand in this, but they should tell you what happens in the real world. You just have to flip it in your own head when you're doing it. So in the variable code, you're looking for column, and then you're looking for row. So as we start counting at 0, the first one is actually 0. So that's the top line in this particular case, and 1 is actually the second line. If you want to turn the backlight off, you use these lines. So we've already looked at these, so I'm going to skip through them now because these are easy enough. These are reference points. So if you want to play around with the code, have a look how to do it. Displaying a simple data. Basic counter. We'll start simple by creating a basic counter project. We're going to run a simple for loop with a range of 500, loop 500 times. For our loop, we'll start at 0, and each iteration will go up by 1. On each iteration, we inject the number using I into our LCD code during the string count with the number I. we clear the LCD each time to make way for new data, the next iteration. Okay, so we copy that, get rid of this, paste it, and let's run it and see what happens. So 1, 2, 3, 4. So as it's doing that, counting up to 500, let's go back to the code. It's going to take a while to get up there, isn't it? 500, and if it's doing it, how quickly is it doing it? Sleep 1, so every second it's counting, so 500 seconds. That's a few minutes away. I'll leave it to it while we look at the rest of it. A basic counter, the example above works, but did you notice a slight flicker for the string count on each iteration? Yep, it's flashing. I maybe can't see it on screen. In fact, I doubt you can. But for me, I can basically tell it's having to redraw it all again. I can tell. Every time it does a number, it's flash, flash. It's very, very quick. And it's just the once every time it's doing it. But I can tell it's refreshing the whole screen. So I bet what it's going to do now is tell us how to do it, but it only refreshes at a certain point. We're clearing the entire screen each time, but the string is static position, so why keep clearing and re-showing it? In this scenario, we can write count just the once before the loop starts, and then just push a number to the display each iteration. We do this by setting a cursor position to column 7 and writing the data from there. This means the count is left alone and the numbers update in the right place every time. It also means we don't need to clear the display each iteration as the numbers overwrites the last in the same position. Okay, they just told us that can get a bit muddly, but okay. So we stop this now. Where we get to? We got to 112. So been babbling on for nearly 2 minutes. Let's play. So how's it done this time then? So sorting it all out and where it's doing it all and what it's talking to. It's going to put count colon space and then for I up to 500, and it's going to keep updating it there. So it moves to 7, prints the output, sleeps for a second, comes back, adds 1 to I, prints it, moves to column 7, prints it, sleeps for 1 second, rinse and repeat 500 times. So let's right now. And now, for me, count is just stationary, there's no flickering. But I can see the digits overwriting. It's not flickering as it's doing it, because it's so quick now, it's only doing that little bit. I'm not seeing like the one flash. I'm sure if it was doing up to, I don't know, 1 million or something, I'd have to redraw quite often. But it's working well. Activity number 4. Displaying current environment data. 'Tis the season to keep an eye on the temperature, so let's do that just by showing the data from our temperature sensor on the display. We'll also show the humidity too. Neat! Every 5 seconds we'll grab the data from our sensor, round it to 1 decimal place, then show the data on our display. We'll show some static text to tell us which value is which, then update the values each time our code loops. We use the LCD dot put string round measurements to do this every one line. This is using the temperature reading, rounding it to 1 decimal place, converting it to a string, pushing it to the LCD. We've seen this kind of thing before in day 9 when we first met our sensor, so it shouldn't be too confusing, right? No, it's not too confusing. We know what we're doing now. We could do anything we want in the code now. All right. Before you give this a try, we need to mention the limitation of our code. Oh, okay. The code could break our code. Our code assumes the temperature will never go down into single digits because if it did, there would be characters left over for the previous value. For example, if the temperature was 10.1, 4 columns, because it would be, wouldn't it? 1 column for 1, column for 0, column for the dot, and column for 1. And it went down to 9.9, 3 columns. The new 9.9 would not overwrite the 1 in the 0.1 bit of it. So you'd see 9.91. We wanted to show you this as a working example of the whole clear LCD thing to show you why it's so important. If the environment's temperature could get that low, you would need to alter the code. The easy way would be to simply clear the display and rewrite the static strings every time inside loop and accept the flicker. There are lots of other ways you could work around this, and I can think of one straight away. But let's stick the code in. Well, read more what it's going to say, and then we'll stick the code in and see what we can do. You may notice that we're now running two I2C devices, temperature sensors and LCD, on the same SDA and SCA pins. Does that not cause issues? Nope, not in the project anyway. Both of our devices are using the same SDA and SCA pins, but as they have different addresses, that's that this bit. That's the addresses, which I said is in hexadecimal. They can be both you can individually. When devices come with the same default address, they can't be changed, then you run into issues. But that's for another day. What other day? We've only got up to 12. We've got nothing else. Right, here's the code. Right, so nope. Let's copy the code, start a new one, paste it. As always, I'm going to state, it's always a good idea to type all this in. As much as it might be a little bit boring, typing it all in, I understand. Believe me, I do. I've gone all the way back to, if anyone maybe remember the Commodore 64, the Spectrum, the ZX81, Amstrad CPC days, or other computers that you had back in the day, I bet there was magazines out there that told you, okay, you can have a game, but you're going to have to type it all in. And then find out next month there was typos and have to wait for the month after that to get the fix. But the point is, do it, because that's how you learn. It's very important. So, yep, we've got all measurements and everything in here. So, I believe the radiators have just kicked in. My heating's kicked in again. So, let's see what temperature we have. 22.6 and 53.4 for the humidity. Does that do anything? No, can't cool it down. Oh well. So it's still too warm in here again because the heating's just kicked in. It's because this is a very small room and it heats up pretty quickly. Right. So that's that on that. We should understand this code pretty much easy enough. We're telling it to print temp, humidity. We've told it where we have to do that. And then we're telling it for the data, only update it there and update it down here. Now, the way I would have got past the example it had as the 10.1 and everything like that, if it gets colder than that, what I would have done is print one character more to the left, and then onto my string add a space. And yes, it would mean it was always writing a space no matter what, but it would, if it did become below when it was using less columns, it would write over that 0.1, it would write over that 1 that's hanging around. Quick easy fix doing it that way. Granted, it'd be left adjusted a little bit, but it's a quick easy fix and no one notices in the code unless you tell them in the code. So the person using it doesn't know, but the code, they go, oh, that's why there's a space. And sometimes it's the only way to do it as well. It's a quick and dirty easy fix. Right, highest and lowest temperature display. The example above is great for knowing the current temperature, but what if you wanted to keep track of the lowest/highest temperatures that our program has seen since running? That's easy. All we need to do is create and maintain update variables that save the lowest and highest temperature values. In the example code below, every time our loop runs, we'll take a temperature reading and show it on the first row of the display. We then use if statements to check if the reading is lower than our lowest record temperature or higher than our highest record. If they are lower or higher, we update the lowest or highest code variables to the new variable then write that to the second row of the display. Give it a try. Some warning applies if environment could go into slight single digits. You may want to clear the LCD and write the static text every update. Right, so I haven't got ice cubes or anything like that to play around with it. Even if I did, I'd be a bit worried about defrosting a bit and getting water over everything. But so yeah, we've got storage now in the realms of the low temp code and the high temp code, and we're checking if the temp now is higher than the high temp, and then if it is, we'll swap it around and everything like that. So the logic is easy enough to get your head around by now. Let's run it, see what happens. Right, so of course it's showing 22.7. What can I do to try to, can I hold it? That going to make a difference? There we go, holding it. Can you see I'm holding it? There we go, I'm holding it. So it's getting warmer now, and it should start to cool down to the room temperature bit by bit. I'm not holding it anymore, look. See, it's coming back down again now. Oh, it went back up again. Come on, get colder. Drying. As you notice though, it's not changing the highest temperature, because obviously it's not higher than the highest temperature, it's going back down again. And the lowest isn't getting changed because it obviously hasn't got colder than that right now. And it's going to take too long to come all the way back down again, but and besides, it's probably not going to go colder than 22.7, because if anything it's getting warmer in this room. But you get the idea now. That's a whole lot of cold we've got there now. But now let's bring our LED strand back into the code. We're going to run an example that shows current RGB color on the display, changing whatever the LDD color changes. To do this, we're going to make use of the dictionary of colors, as we use the key to both provide the RGB color as well as the color name, text/string, for the display. Handy. Here's our dictionary called My Colors. Feel free to add more. We'll just stick with that at the moment because I'm trying to get on with doing this. But what you could do is go to the older code and pick up all the ones from what they had before with the, what was it? The aqua and all that fun colors that they had. We use this for a for loop to iterate over the dictionary for I in our colors. Then we use I, which will be a key of the color, red for example, for the LED strand to fill the color of the LCD text. Strand fill references the dictionary requesting the value associated with the provided key, I. So that makes sense. We've done that sort of stuff before. The LCD code can just use I directly as the keys in the name of the color. So we can use the string. So we're going to display what the color is on our display. There's only one catch. When you iterate over the dictionary, it's not in order like a list. You can add some code to the order things, but it's probably a bit too complicated for the first 12 days. For the curious and brave, look up the sorted, open bracket, close bracket method using lambda. Okay, let me know if you're that brave and let me know what your outcome was. Try the example below in the normal way. Okay, so we'll get rid of this, start a new one, copy the code, first paste, and run this code. Oh, strand color blue, white, red, and green. And it's going back to blue. So as you can see, the screen is staying the same colors it is, but it's updating what the colors are, and you can tell just about from the LEDs. They all are lighting up like they're supposed to. So we've got a physical display telling us what should be happening, and we get to see with LEDs of what is actually happening. Right, activity number 7. And we'll stop that code for a bit because it's a bit distracting. I'm actually going to unplug it as well because it's quite bright. Just unplugging it, plugging it back in again. I press stop so it finds it. Right, activity number 7, the random color finder. Are you trying to find some cool RGB colors to use in your code, but you're not sure what the RGB values to use? How about a little program to show you a random color on the LED strand, then display the RGB values on display for you to take note of? A neat little program and another great excuse to use random. Our code creates random RGB values, pushes them to LED strand, and then displays the individual RGB values on the LCD next to the R, G, and B. Easy! If you need more time to write down the RGB values, just increase the delay at the end of the loop. Okay, so get rid of the old code, start the new one, copy, paste, and run. So we've got R58, RG725, and R222. So interesting colours. Let's zoom out a little bit, just a little bit, so that we can see. Actually, maybe not all the LEDs will make it easy for the camera to keep up. So it's pretty much looking all white at the moment. It's a bit pinky coloured. So if you wanted it to slow down a little bit, you could change this 5 seconds to 10 seconds. It would take you a very long time to find a nice colour. Right, what does it say at the end of all of this? Scrolling text. Right, let's stop that code then. Let's finish with some scrolling text. Making information scroll across the display means you can show longer strings and more data, which can be really handy for some projects. We manipulate strings to give us the impression of scrolling data. We create a function to do all that hard work for us, then call that function with our string as the argument. Before we explain everything in detail, run the code below whilst having a read through the commentary, then carry on reading below for some explanations. We've added a print line as we feel this helps to understand what's going on. Okay, so we stop that. Well, close that rather, start a new one. Copy the code, paste, run it. Scrolling the text. It's a bit hard to read because it's overwriting. Last bit. Not very clear to read. You can read it, but it's up. But as we can see down here as well, that's basically what's getting put across. But it's horrible. It really is horrible to try to read it, because as I was saying before, when you overwrite the same spot, it basically, if the pixels are being used before, they stay lit, but if they haven't, then they're getting turned off and other ones turned on, and so it works, just not very nice to look at. Probably looking better on the camera than it is in real life. Anyway, so what have we got going on in the text? Setting it all up. Add 16 blank spaces after our string. So, okay, so there's the 16 blank spaces. While true, move 0, 0. And then sleep time, we're updating every half second. Show the first string characters in the string. I think the LEDs are still on from last time. Let me just unplug and go back in again. There we go. All right, but even so, the updating is horrible. Probably just the timings of things. Anyway, we've got text equals 1 colon plus text. I wonder if that 1 means whatever it is plus whatever there. Right, so 1 colon removes the first character. Oh, so that's what it is. So it's removing the first character. Let's see if it helps if I should read the commentary on it. So scrolling text summary. Here's how our scrolling function works. We give the function string an argument. We add 16 spaces to the end of the string. We then start the while loop. Every loop we force the display to move back to the position 0, 0. We show the first 16 characters of the string on display. We add the delay, remove the first character of the string and add it to the end of the string using the slice operator. New thing alert, see below. At the very end of our example code, outside of the function, we call this function and add the string we want to display to the bracket as the argument for the function. Okay, I can see what's happening, but well, actually we can physically see what's happening because this is what's getting displayed. You just pick a line and you can see that's what's getting pushed. So we're getting the impression that text is getting pushed across there. What is a slice operator? We're using a slice operator to manipulate the string we pass to our function. But what is this? Slice operators help us chop up strings, taking slices from it and doing things with those slices. We use the string's variable name followed by the square bracket and add different things inside these brackets depending on what we want to do. Here's a few examples you can run. We'll make a string called myString and print it with some slice operators. For example, if you want a number to the right of a colon, it will return that number of characters from the start of a string. Try this. Okay, so we need to stop this now. I'm going to copy this, stick it in here, paste, press enter, and there we did. So we only wanted the first character, wanted the first 2 characters, and we wanted the first 3. Example 3, if we want the number to the left of the column, we remove that many characters from the start of the string. Try this. So this is going to be the other way. So we press enter. So this time the characters, we had 5, didn't we? Because we have H, E, L, L, O. But we want to remove the first one. So it's got dropped the H and left us with the last 4 and displayed them. Then we want to get rid of the first 2. So H and E disappeared this time. And then 3, the first 3 characters, H, E, L. So that's easy enough to understand. If you just, example number 3, if we just enter a number inside the square brackets, it will return the character from the index of the string, like this. So enter, we end up with HEL. So suddenly we're counting from 0. So we want the very first one, and then 1 and 2. So if we use the colon, we count the way that we would normally count. If we don't use the colon, we count the computer way, which is starting at 0. Okay. Our slice operator. We use slice operators inside the line to the example code. So we've got that code. We found this, didn't we? It's here. There it is. It takes the existing text variable, removes the first character with text 1 colon, and adds the first character to the end using text 0. So we've always got the same. We've still got the 6. Basically, it's chopping off what it was and then sticking on the end. So it gives the impression that we're looping it round. Questions you might have. Why do we add 16 blank spaces? If we didn't, when the string scrolls, we get the last character it shows, the last first character, the next to each other. Watch the print lines as the program runs, the gap it creates. Comment that line and watch what it prints. Okay, so so I'm going to comment out this now, line number 23. We put a hash symbol in, that comments that. So now we're getting rid of the 16 lines like it's just told us to do, and then see what happens. So on line 23, just stick a hash symbol there. See, suddenly it looks really ugly because there's no spaces at all. It's not given a chance for it to look like the whole sentence has scrolled off the screen. That's why. So we stick it back in again by deleting that hash. It looks like it's working because what we have, we find the code. We have scrolling text. Where is it hiding? We have scrolling text. Here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And of course that makes sense because there's only 16 characters on the display, if you remember. So that's why we're doing it, so that eventually we're filling up the whole screen with 16 spaces. And it carries on going. So it gives the impression that we're scrolling when actually we're not doing. Or we just take the W, remove the W from it says we. I'll try to display it, say it as it's coming across. It should make perfect sense by now anyway, but just in case it doesn't matter. We all learn at different rate speeds. So we've got the W, we're taking that off and moving along, taking it off, moving it along, taking it off, moving it along. And what we saw there though as it doing was actually the spaces it was getting rid of. So, and as the spaces come back on again, that fills the gap to make it look like the rest of it's finished. Why do we manually set the LCD back to 0, 0 each loop? We're letting the characters overwrite the previous ones without clearing the LCD first. If we don't let the position each time, the program will try to write the following loop characters next to the last one. So, you know, it would bang it. If it had the display long enough, you'd have to have one that was sticking down the street. And of course, then it wouldn't scroll, it would just be printing it all the way along. Comment out the LCD move line to see it for yourself. Okay, let's do that then. Where's the LCD move? Comment that one out now. Let's run it again. See, that's what you end up with. Basically what we're seeing in the shell box. To end up with two lines of it. I'll take that back up again. And run it again. Why do we remove the first character and add it to the end? We remove the first character and then show the updated string on the next loop. This makes it look like the text is scrolling. I've already explained that bit. We keep adding that remove character to the end of the string to keep the string showing the same text forever. Watch the print lines as the program runs to see it in action, as we've already said in the shell box. Sorry. What does the asterisk do to the text? Times 16 asterisk quote quote, all that stuff there. This is simply a multiplication operator. It's a 16 times a space, which is a blank space 16 characters long. We could have used well, basically 16 spaces, but the operator operation is cleaner. So why type it all out when you don't have to? Make the computer do it. Though sometimes it is actually better to do it all in one go. It can make it faster, but the stuff we're playing around with here, it doesn't really matter. That's for when you become a fantastic programmer and make programs I wouldn't even understand how to do, which is pretty easy to do. But anyway, day number 12, complete. LCDs are fun, right? We've shown you the basics on how to use an LCD with the library along with a few little tricks. Now it's over to you to come up with the cool projects that display data in fun ways. Recap time. What did we cover on day number 12? How to wire up an LCD with the I2C backpack, using multiple I2C devices with different addresses, how to use an LCD library, when to clear an LCD and when not to, showing sensor data on LCD displays, slice operator, scrolling LCD text, our usual reuse of newfound knowledge. Hello there, random. Over to you. That's it, folks. It's the end of Let It Glow. We know many of you wanted this to last an additional full 25 days. However, like the previous year, there was a previous year? Ooh. We wanted this to continue as affordable and accessible to many people as possible. We really hope you've enjoyed following along each day, and we really hope you continue your journey as a maker using your selection of Blinky bits and other components to experiment and making fun projects with. We've covered the basics of what's possible with the fantastic little microcontroller and the components you've discovered over the last 12 days. But there's so much more to learn and experience. If you would like to expand your selection of components for the Pico, the store is full of goodies. Be sure to check out the dedicated Raspberry Pi Pico section too. Maybe you'll progress to the Pico W with wireless capabilities. Ooh. More resources. The internet is jam-packed full of projects and examples using the Raspberry Pi Pico and MicroPython, and 99.9% of this information is free, so don't stop now. We've even had some great examples from our makers in comments section of the calendar along the way. Giles is doing some really cool stuff, check it out. Search engines are your best friend when it comes to making and coding. Forums, blogs, tutorials, social network user groups, and more are at your fingertips and hold endless amount of examples, code snippets, previous discussions, and useful information. A good starting place for inspiration and a great community is the Raspberry Pi forum, specifically the Pico section. Just don't forget to always search before asking a question. That's all, folks. Have a Merry Minkless and a Blinky New Year from everyone at the PiHut. What can I say to follow that? Go into the description, check out the links for Discord and Patreon. Don't forget to hit that like button, the subscription button, and that notification bell. Who knows what's going to be next? But as always, happy gaming. Oh, and happy holidays, Merry Christmas, Happy Hanukkah, whatever it is you. I don't know.